Okay, hi everyone. Um, if you came to lecture on Monday, I forgot to record, so I'm re-recording the lecture for everyone who wasn't able to make it. Because this is like a pretty important topic that will come up in your final projects. So hopefully this is helpful. So this lecture talks about like the basics of curve fitting, and we'll go over like a quick code demo on some of the basic statistics behind it and on how to fit a line to some data. So to get started, let's talk about what data kind of really is. When you look at data, sometimes it looks like it has a shape, like it looks like it might be a line or like a parabola, but it's important to remember that data is really just a set of X and Y points. Regardless of what shape it looks like it has to you, it's really still just a list of X and Y points. So it doesn't really mean anything inherently until you've analyzed it and drawn conclusions. So the purpose of this lecture is to kind of introduce us to some tools we can use to reach conclusions and predictions. So when we look at a plot of data, there are some things that as humans we're better at doing than computers. Like for example, if I showed you these two plots, then you could probably tell me, like for example, this one, you could probably say, that looks pretty clearly like it's a straight line pointing downwards, or that this parabola is, it's concave up and it probably has an intercept around, whatever. But to a computer, these are still a list of XY points. So there's no like shape to the computer. It's only the shape in your mind. But if you wanted to actually quantify the relationship that you can see intuitively, that can be a little bit more difficult depending on the complexity of the function that you're seeing. And these are pretty easy. Like it's a straight line and it's a parabola. They're both functions that we've all pretty much studied pretty extensively in school. But then lines can get kind of complicated. So like this one would probably be a little bit more difficult for you to quantify as in like give the like exact equation for, even though you can pretty clearly see the shape of the data. So this is something that computers are really good at. And we're going to go into like how we can use computers and Python packages to do this for us. So we can start with like some of the intuitive background behind curve fitting. So if I gave you the same scatter plot that we've seen already, and I said, I want you to find an equation for it, how would you go about trying to do that? And I think a lot of us would say, I would draw a line through it and try and get as close to as many of the points as possible. This just like intuitively makes sense as like, well, I want my line to like, well, to represent the data well. So if it's as close to as many points as possible, then it makes sense that it would represent the data in like a pretty thorough way. And that is actually like the basis behind curve fitting. Where like more formally, curve fitting is the process of fitting a mathematical model to a data set. And once you fit a model to it, you can use this to quantify the relationship and you can predict values, which is usually like the more like useful thing to do with curve fitting. And you generally want to find the best fit model, which is the one that, like I said earlier, gets as close to as many of the points as possible. So it minimizes the error. And we'll get into error in a second, but error is the distance between each of your data points and the prediction line that you made, so your model equation. And overall, you can measure the fit by summing up all of the errors over all the measured data points. So we can look at an example of what error looks like. So here are some pictures from the Data 8 textbook. So if you think this kind of stuff is interesting, feel free to go take Data 8. It's a really cool class, and I recommend it. So here we have 3 different lines. And so the fit line or the model equation is in light blue, and the data points are in this kind of like dark blue color. And the red bars going up and down are like visual representations of the error. So if we just kind of look at these, we can see that like some of these lines are better fits than others. And if we specifically look at the red bars, we can see that like this plot down here has really big error bars. And also the line just like doesn't look like it fits. But we can see that the line doesn't look like it fits and the errors are huge. So this is a pretty good sign that this is a very bad model. Whereas this one at the top looks like it goes through the data pretty well. So visually that looks good. And the errors are the smallest out of all the plots that we're looking at. So that's also good. So that's also, those are good indications that this is a good fit. Here's like a little practice problem to get like a little bit more familiar with calculating errors over like an entire data set. So here's a few XY pairs. So this data that I've given you in the table is like your observed points, so like your collected data. And then this model equation up here, y equals 10x plus 3, is like the model equation we're using as like our fit line. It's like the light blue line in those previous plots. And then here's an error formula that we can use to calculate the error over this entire data set, where it's 1 over the number of points times the sum of the difference between the observed points, so these data values, and the expected value, so the y value generated from this model equation, squared. So you can think about how you might calculate that using either like you can do it by hand or like using Python. And then I'm going to go over how to do it in Python really quick, because this is like a calculation that comes up very frequently. So let's go do that. Okay. So let's calculate our error for the data set that I showed you. So first, let's start off by, that's for later, importing NumPy, because we're going to use it for this. And then let's put in our observed y values. And then in here, we're going to put all of our different y values that we saw in order. And then let's also define our model equation in here. And we saw that that was 10 times x plus 3. So now we have our, plus 3. So now we have our observed y values, so our data values, and then our model equation. So the next step would be to generate predicted y values for each of the x's that were there. So let's define our x's. This is also just from the table. So we had 0, 5, 3, 1, and 7. And then our predicted y values, I'm going to call them y hat, because that's like a pretty standard notation for predicted y values, where the hat means predicted. And let's just apply our function of x to all of these x values. And then we can like take a look at what that looks like. So these are our predicted y values, and then these are our actual y values. So if we want to calculate the error, then we know that we want to take the sum divided by the number of points, and then the square differences. So we can recognize that that is actually just the mean. So we can use np.mean. And then we want to subtract our two arrays. So actual data first, and then our prediction second, and then square this. And we get 102.8, which is pretty large. So you can guess that maybe our predicted values aren't that good. And if we kind of look at these, we can see, yeah, these are not that close. And we can look at some formulas for error. So we might recognize mean squared error as the one that I just showed you. It's the average of the squared differences. So the average squared error. And then root mean squared error. Let's move this really quick. The root mean squared error is mean squared error, and then you square root the whole thing. And this is useful because when you're calculating mean squared error, you end up squaring the units also. And so the resulting number can be a little bit difficult to interpret. Like you've like dollars squared, and so that doesn't really make any like physical sense. So when you take the square root of that and you put the units back into something, that makes more sense. Little quick aside for chi-squared. If you've seen chi-squared before, you probably saw it for categorical data. So this one is different. This is for numerical data. And it's similar to what we calculated before for error. You have the sum of all of the pairs of points predicted and observed, where it's observed points, so the actual data, minus your predicted value given your model equation. And then you divide it by the error at that point. And then you square that, and then sum all of them. So it's slightly different. Reduced chi-squared is a related concept where you take the chi-squared value that we calculate using this formula, and then you divide that by the total number of points minus what's called the degrees of freedom. Or the degrees of freedom is a number that's equivalent to the number of fitted parameters, where the fitted parameters is like the number of parameters in your model equation. So if you have a linear equation, then your two parameters would be the slope and the intercept. And we're going to get into that in a little bit longer when we get into SciPy, which we're getting into right now. So some useful packages for curve fitting are numpy.polyfit. This is really good for fitting polynomials. It's very like intuitive and easy to use. It takes 3 arguments, your x points, like your data and your y points. Again, also your data and then the degree of polynomial that you want to fit. So if you want to fit like a parabola, then you would say degree 2. And if you want to fit a cubic, you would say degree 3. SciPy.optimize.curveFit is the one we're going to be using more extensively in this class. That's because it's a lot more general. You can fit any equation that's not necessarily a polynomial, which can be really useful. So this one takes 4 arguments, and we're going to go through like what each of those are in a little bit more detail in a second. But it takes in the model equation, which is kind of like we did when we're calculating the error, we defined a function that returned 10x plus 3. So some like general form of mathematical equation. So it could be like a general polynomial, like a general linear equation where you leave it as like mx plus b, or ax squared plus bx plus c, something like that. And then like polyfit, it takes in your x and y data, and then something called p naught, which is your initial guess as to what you think those parameters in your equation are. And the purpose of P0 is to kind of give the algorithm a place to like start looking for good fits for the model and like how it can reduce error. So let's do a demo really quick so we can go over how to like actually use SciPy. For this demo, we're going to like randomly generate some data, and then we're going to fit a straight line through it as like a simple example. So let's import our packages. You imported NumPy already, so we can skip that one. And let's import our plotting stuff. And then our curve fitting package. And I'm importing it as fit. As far as I know, there's no like super universal convention for this one, but fit works. So we're gonna use that one. And then let's start by generating some data. Another way to think of data is kind of as like a noisy representation of a true relationship. So if we like start at a model equation and then kind of work backwards, we can imagine that we like start off with a bunch of points that lie exactly on like a parabola. And then we take those points and we flick them off like one by one in either direction. And then when we take away the quadratic, we only see the data. So when we looked at like some of those plots earlier, that was like points that are like vaguely in a parabola shape. One way to think about that is that those data are like noisy, like a noisy sample from the true relationship, which is the parabola. So we're going to use that concept to generate our data in this case. So we're going to start with a true relationship, which is a straight line. Let's just set a slope of 0.5 and an intercept of 3. Completely arbitrary. And then let's say we want 20 points, because that feels like a good number to me. And then let's make some x values. Let's say I want 20 of them, where we have 1 for every unit interval. And let's generate some y data that's like a noisy straight line. So we're going to start with our slope and our intercept. So this would just generate data perfectly along the straight line. That's super boring. There'd be no point in fitting a line to it. So we're going to add some noise. And we're going to do that by utilizing this function, which generates noise according to like a specific distribution, the normal distribution. It doesn't matter too much, but we're going to see what that looks like in a second. So let's plot our data so we can get a sense of what it looks like. And this is always like a very important step to do when you're curve fitting or like analyzing any kind of data. Just always graph it first before you do anything. We can see that I didn't run this. There we go. So here's our noisy straight line. And we can run it again and see that we'll get like a slightly different graph. I actually had something blocking the screen, so I don't know if that's different, but I choose to believe that's different. Yeah, that is different. Okay, great. And here's the data we're going to be working with. It looks like it's like a noisy straight line. So but if we didn't know that, we're going to pretend that we didn't know where this data came from. This looks pretty linear, so we're going to fit a straight line to it. So let's start going into the SciPy function. So the first thing that I said that this function needs is the model equation. So let's make one. We're going to call it f. The name doesn't matter. But what does matter is that the very first argument in your model function is x. If you put anything before x, it's not going to work. So x has to go first. And then we know a linear equation is y equals mx plus b. So there's 2 parameters, m and b, the slope and the intercept. and we're going to return the general form of the model. So this would be m times x plus b. And then that's it. That's the entire model equation in this case. If we wanted to do like a quadratic or something like that, we could do where this is like the general form of a quadratic equation. So everything's a variable except the numbers that dictate the form of the function. So next, let's come up with our guesses for P naught. And again, P naught is like, if we look at the data and I think that this is like a noisy representation of a straight line, where do I think about around the values of the parameters are? So like about what do I think the slope is? And like about what do I think the intercept is? And I'm going to pretend that I didn't generate the data myself. And I'm going to say that the slope looks like it's like 0.37, because I'm really good at estimating maybe. And then I think the intercept is at like, it looks like it's at 2. I mean, 2 is right there. I don't know why that took me so long. So the intercept looks like it's at 2. And run that. And now let's actually run the curve fit function. So the curve fit function actually returns two things. It returns the parameters, and it also returns something called the covariance matrix. The covariance matrix includes all of the squared errors for the calculated parameters. And we'll like go into how to extract those in a second, but it's important to capture both of those outputs separately. So we're going to set up our return like this, and we'll run our function. And we imported our library as fit. So we're going to do fit.curveFit. This is the name of the function. And we're going to give it our model function, which we call f, our x data, and our y data, and our initial guess. And then we can run this. And let's take a look at these different outputs. So let's look at parameters. And this is a 2-element array where the first element is m and the second element is b. So this is what SciPy's curve fit function calculated as the optimal parameters for this model equation. And they're in the same order as when we fed them into the model equation. So if we switch these, and also these, they're switched. So they go in the same order. We'll put them back because this is going to confuse me. You may also notice that like I left the initial guesses swapped. And in this case, and for polynomial functions in general, your initial guesses don't matter too much. For more complex functions, you will have to be more careful about the values that you put in. But for simple functions like this, it's totally fine to like be a little bit off. Let's look at our covariance matrix next. And this one is a little bit more interesting because it's a 2D matrix. And the squared errors for each of our parameters are along the diagonals. So there's one here, and then there's one here. And these are also in the same order as the order we fed them into the model equation. So the first squared error is going to be for m, and the second one will be for b. So this is the error for m, the squared error for m, and this is the squared error for b. So let's go and like extract all of our things and save them as variables to make it a little bit easier for us. So I'll call this m, and we're gonna have some like redundant names floating around, but it's okay. And this is the first element of the parameters array. And b will be the second element in the parameters array. And then we'll pull out our errors too. So we'll say the first top left corner of our covariance matrix, so the first diagonal element is the squared error for m. So we'll square root it. And then we'll do the same thing for b. And then we're going to get the next diagonal element for this. This is the bottom right element. Yeah. Okay. So the next thing that you should always do when you're doing curve fitting or any kind of like linear regression or anything like that is to plot your data with the line. if you can. In this case, we can. So let's use our model equation to predict some additional x values, kind of like what we did for the error problem that we went through. So let's just define some like arbitrary x values. This is going to give me 100 points between the minimum and my actual data and the maximum in my actual data, just to like make sure that my arbitrary values aren't like totally going to the sides of my graph. And then let's make our predicted values. We're gonna use our model equation. Just feed in everything that we pulled out earlier. So these two. And then let's plot everything on the same graph. And this is what we end up with. So that we can see, this looks pretty good. This looks pretty good. It goes through the middle. There's nothing crazy happening. So I'm pretty satisfied with this. We can look at one more thing, and we'll get into that when we cover the next part of the lecture, which is linear regression. Okay, so let's go over linear regression really quick. This is going to be like a really like broad overview, but linear regression is like a special case of curve fitting. We just did it. It's where you only fit straight lines to your data. So it's important that your data looks like it can take a straight line first. But linear regression equations, you can calculate them without having to really use like a numerical algorithm like SciPy's. They minimize error by default. So if you use the equations, you're guaranteed to get the best fit line for your data, which is pretty cool and like very useful. Get rid of this. So let's go over R and R squared really quick. R is called the correlation coefficient. It might also be called like the Pearson correlation coefficient, but it basically measures the spread of your data set. It's contained within the values -1 to 1, where the sign matches the slope of the data. So negative R means it's a negative slope, and it's a positive R, it's a positive slope. The sign of R, I just said that. But if R is close to 1 or -1, then it means that the points are like very close to basically being lying on a straight line. So if we think about our noisy representation where we flick the points off in another direction, they wouldn't have been flicked off very far. Whereas if R is very close to 0, then for linear data, it means that we really flicked them a lot, like we really went for it. However, it's important to note, and I'm going to show you some pictures in a second, that just because R is close to 0, it doesn't mean that there's no pattern at all in the data. It just means that there's no linear pattern. So if we look at these, we can see that in one of this is like a slightly different type of plot. But this would have an R of 0. But there's clearly a pattern in the data, right? It's like a parabola. But R is still 0. So it's telling us that there's no linear relationship, and that's true. But it doesn't mean that there's no pattern in the data whatsoever. The second one shows like a cloud of data. R would be 0 in this case too. And in this case, there is basically no relationship. Here's some graphs that are also from the Data 8 textbook. If we were to rank these in like order of largest R, like absolute value of R, so the smallest one, we would start with this one because the lines are like the closest to lying on a straight line. Like we didn't flip them very much. And this would have the smallest R, sorry, because the points are the closest to just being in like an amorphous cloud. The general stuff to look out for when you're doing any kind of curve fitting is essentially overfitting and underfitting. Overfitting is when you apply like a really complicated model to your data. So like we can use the example of like, for any n number of points, there's guaranteed to be an like n degree polynomial that passes through every single point. So your error in this case would be 0 because every single point is predicted at the same value. But if you were to try and use this equation to predict for an unknown x value, it would probably do like a pretty bad job because it's so specialized to your particular data set. So like what this point says is, like if your model equation has like a ton of parameters, like it's the same as your number of data points, then that's like way too many. because it won't predict well for unseen values. The opposite issue is underfitting or oversimplicity, which is when you fit like a much too simple model to it. That'd be like if you try to fit like a straight line to a parabola. Like that also isn't really representing your data very well. And it's skipping over a lot of the important trends. This is why it's like super important to plot your data first. You can get a pretty general sense of like what's going on. And then specifically for linear regression models, you always want to make sure you check the residual plots. And I'm going to go over that in a second. Residual plots like really magnify patterns in the data. So if your residual plot has a pattern or a shape, then it probably means that a straight line is not an appropriate model to use in this case. And you're better off looking at like slightly different model equations. Good residual plots will look like clouds, like there will be no pattern at all. And that means that your linear model is appropriate. Here are some examples of residual plots. So we can see that we have the predicted values on the x-axis, and then residuals. Oh, no, sorry, I'm sorry. This is the original data like plot of the data. But it looks like a straight line. Like it looks, there might be like a little bit of curve to it. But that looks pretty straight. So we fit a straight line to it. This one looks pretty good. And when we like plot the residuals, whereas this is the predicted y values, and then we have the residuals on the y-axis, there's like a very clear pattern. So this implies that maybe a straight line isn't an appropriate model in this case. Whereas for the other example, we have like a pretty like linear looking plot. We put our line through it, and then we graph the residuals, and it looks like a cloud. So that means that the linear model is appropriate in this case. And then this is a link to the chapter in the Data 8 textbook that I took a lot of these pictures from, not all of them. So I like to go through making a residual plot really quick because we have a straight line and some data. So let's take a look. So if we want to like really accurately calculate our residuals, we should have a predicted y value for each of the x points that we put in. I think we call those x data. So let's calculate these, because this would give us a predicted y value for each of our x data that we put in. So that's what this looks like. And then our residuals would be our y data, so our original data minus our predicted values. And then let's plot our residuals versus our predicted values on one graph. And we want our predicted values to be on the y-axis, and then our residuals to be on the, so our predicted y values to be on the x-axis and residuals to be on the y-axis. That should be scattered. Okay, so that looks good. There's no pattern. It looks like a cloud. You don't have that many data points, but it looks like a cloud. So we did a pretty good job. And that's like what residual plots look like. So if we look at this like zero line here, and if we were to trace that across, that would be like taking our predicted line and then just kind of like yanking it flat. So it like magnifies all the distances relative to the regression line, which can be really helpful. So that's all for this lecture. On Wednesday, you guys will get to do some problems, and then for the homework, you'll get to do more problems. So hopefully you'll feel pretty good at this by the time the final project comes around. But let us know if you have any questions. And thanks for watching. Bye.